So now we know that if it had 0.195 joules of energy at its most compressed state, oh shoot, I forgot about friction. This question is really neat. So let's do free body diagram really quick. So we've got gravity going down, we've got normal force going up. They're going to cancel each other perfectly, but they're going to be both equal to mg, which is going to be well actually, let's go ahead and do mg as if the bullet is already inside of the block. So it's just going to be 1 times 9.81. Yep, so it'll be what's called 9.8 newtons. 9.8 newtons. They cancel each other, but there's also another force that's going to resist the block sliding that way. And so it's going to push this way. That's our friction force. Coefficient of friction in this question was what?
0.5.
0.5?
Yep.
So friction is always equal to the coefficient times the normal force, so it'll be 0.5 times 9.8.
Which is 4.9.
4.9 newtons. Okay. All right. So this is where we're at. We're trying to figure out how much kinetic energy the block and the bullet had right as the impact happened. So we're going to go ahead and kind of break this big problem into a smaller problem, and we're going to say we just want to look at from the moment of the impact to the moment where it was as compressed as the maximum compression, what happened from that beginning point, that initial point, to that final point. So we're going to say energy initial, and all of its initial energy would have been kinetic energy, equals energy final. All of its final energy would have equaled this spring energy, potential energy. But because we've got this friction that we need to take into account, we can't just say energy initial equals energy final, because energy is not being conserved perfectly. What we can say is energy initial equals energy final plus any work that was done. In this case, the work's going to be done by the friction. Good.
Yeah.
And then we also know that work equals force times distance. And we already know the force of the friction. And we know the distance over which the friction acted, because it's going to be that whole change in x. So we can say 4.9 times 0.051. That comes out to be
0.249 or 0.25.
0.25. 0.25 joules. Okay. So, plugging into this then, we know that the energy final was that spring energy that we just solved for. So that's that.
Okay.
And the work we just solved for
Plus
is that.
0.195 plus 0.25.
Good. So if we plug those guys in, 0.195 plus 0.25.
0.445.
0.445. So the initial energy, right when the bullet and the block made contact with each other, they must have had 0.45 joules of energy.
Okay.
Because we know that at the end, this much work had been done and this much energy was still left in the block bullet system. So they must have started with this much. Does that make sense?
Yeah.
Okay, so now we're going to take this number and say, since we know all of their initial energy must have been kinetic energy, we can say they must have had 0.445 joules of kinetic energy. So we'll take that value and we'll set it equal to the equation for kinetic energy, which is 1/2 mv squared.
Can we solve for the v?
Yeah, because we know the mass is 1, and we can solve for the velocity.
So,
Let me know when you guys get
I
something.
got 0.4717.
I got 0.943.
I got 0.943 as well. Let me double check it. So if we divide, so we take 1 times 1/2 is still 1/2. If we divide 0.445 by 1/2, it's the same thing as multiplying by 2. And then if we take the square
Okay.
root,
Got it.
you got it too?
Mhm.
Yeah, I got it on my second time. 0.9.
434.
943 meters per second equals velocity. Cool. So now we've done everything that we need to do with energy, and that was no small feat, right? So now that we have velocity of our block and our bullet system, and we have the mass of our block and our bullet system, we can find the momentum of our block and our bullet system. So now we can start looking at this idea of momentum initial equals momentum final. Momentum final being when the block and the bullet are now stuck together. So let's do that work up here, momentum initial.
Okay, really quick, because it
Yep.
asks for the initial velocity, so I would think that this velocity we just solved for would have been
So this is the initial velocity of the
The
block
block.
after it's been hit by the bullet.
Okay.
But we want the initial
You want
velocity
it
of the bullet.
Okay.
So yeah, it would be easy to say, oh, I found a velocity,
Yeah.
hopefully that's the answer. But if we just kind of like think about it, obviously no bullet is gonna be traveling at,
Yeah.
just under a meter per second.
Yeah,
That's pretty
okay.
slow. That's
Yeah.
really slow.
That's really slow. Okay.
So now we can use this information though to backtrack, kind of reverse engineer our way to the original velocity. So we know momentum initial was just the mass of the bullet, so we can call that m1, times the velocity of the bullet, v1. We could say m2, v2 of the block, but we know its velocity was 0 initially, so that's just going to zero itself out. And we know momentum final is going to be, now that the block and the bullet are stuck together, it would be their combined mass times their combined speed.
Okay.
So we can call that m2, v2. So if we start plugging in, mass of the bullet was 0.001. Velocity we don't know, that's what we're looking for. Mass of the combined bullet and block is 1. Velocity we just solved for is 0.943. Now we can backtrack and solve for velocity.
So you just divide the 0.001 over.
Yep.
Yeah.
So V equals 943.
940 meters per second.
I
Got
gave
it.
it to you?
Yeah. Okay.
Cool. That's pretty fast, actually, so I
Yeah,
was kind
that's
of
really fast.
skeptical. Because I know in the past when I've done this type of question, usually it comes out to be like 300 or 400 meters per second. But I
Okay.
guess this bullet is just
Really
Pretty
fast.
fast.
speedy, yeah.